So in today's session, we will start with a new topic that is spanning tree protocol. But before we jump into the discussion on spanning tree protocol, what is it about, or why is it used, or what is its purpose, and how is it helping the helping in the networking world? Let us just discuss one of the most important factor or most important loophole in the networking side. So once we understand that loophole, okay, we will understand why spanning tree was developed. Okay. So as I said, before we start spanning tree, let's understand that loophole. And with that loophole word, the word that comes into my mind is itself the word loop. Okay. So what is your understanding of a loop? Not from a networking point of view, but from a general point of view. What is the meaning of the word loop? It's general. You can just tell me the general dictionary meaning as well. Okay, it's not necessary. It has to be related to network. What do you
Actually,
understand
loop
by
is
loop?
like something keeps on rotating. Some work is their task. It is keep on going in the same way. Suppose once you start
Okay,
some task, you go to shop and bring something. Like it will keep on going.
right.
You will go to shop, bring, go to shop, bring like that.
Repeat.
If anything in the like switch, suppose you start a traffic, it will keep on going, going, going. Like that. It will not even stop anytime. So and then
Exactly.
like that.
Exactly.
And something you start moving something in a like circular. Take a rope and tie a stone and start circulating. It
Yeah.
will keep on going like
Right.
that. Like, it's continuous movement that is there is no stopping of that.
Correct. Correct. So basically, this is our general understanding of what is a loop. So similarly, in your layer two network, when I say layer two, I have discussed this many times. When I say layer two, I am talking about the data traffic which understands only MAC addresses. Okay, which have MAC addresses as the forwarding mechanism. Okay, we know that switches use MAC addresses to forward data. Right. So when I say layer two network, I mean the devices use MAC addresses to forward data. So in such a layer two network, how does a loop happen? Okay, we'll try to understand that. Okay, so let's assume there are three switches: switch number one, switch number two, and switch number three. Okay, and they are interconnected like this. And each of these switches are connected to different PCs: PC number one, PC number two, and PC number three. Right. And again, PC one's MAC address is 1111, PC 2's is 2222, PC 3's is 3333. Right. These are the MAC addresses. And again, just the same way, we will assume that the MAC address table of these switches are completely empty. Okay. So MAC address table of switch number one is empty. There are no MAC addresses, MAC address detail present. Similarly, for switch number two also, the MAC address table is empty. And for switch number three as well, the MAC address table is empty. Right. Now,
Sorry, sharing
let
your
me.
screen. Nothing is coming.
Oh, I'm
See,
sorry. I'm absolutely sorry. I think I am. Okay, let me share once again.
I thought you were speaking and suddenly it is like
No, I was actually sharing. Can you see now? Can you see my screen now?
yes, yes, it is coming now. It is one, two, and three switches there. And one is two
Yeah,
is connected.
correct. Yeah, yeah.
Again, one more two is connected there, right? So what is it? Two.
Yeah, so there are three switches: switch one, switch two, switch three.
Okay, and they put handle
Okay,
PC1, PC2, PC. Okay, got it.
PC1, PC2, PC3. Okay, and as I was saying that the MAC addresses of these switches are empty. You can see the MAC addresses on the sides of the switches. Okay, so let me also write down the interface numbers. Okay. One, interface number one, interface number two, interface number three. One, two, and three. This is interface number one, interface number two, and interface number three. Okay. Now, let's assume that PC1 sends a data to PC number three. Okay, so the source MAC is going to be 1111, and the destination MAC address is 3333. 3, 3. Okay. This is the data that PC number 1 sends. So when PC number sends, PC 1 sends the data, switch 1 will receive it. Correct. So when switch 1 receives it, it will make an entry for it saying that I have received a data with a source MAC of 1111 on my interface number 1. Okay. Then it looks for the destination MAC address in the MAC address table. It does not find. And we know that when a particular switch does not see the MAC address in its MAC address table, it is going to flood it out of all the interfaces. Right. Now, let's go from a clockwise perspective. Okay. So switch 1 sends this data and it is received by switch number 2. Switch number 2 makes an entry for it. It says that I have received a data with MAC address 1111 on the interface number 3. Right. It also reads the destination MAC address 3333, which is not present in the MAC address table. And hence, it is going to forward it out of all the interfaces. Now, now switch number 3 receives this data. Okay. It will also make an entry 1111, right? And it will make an entry for interface number 1. And it again will not see the destination MAC address, that is 3333 in its MAC address table, and it is going to forward it out of all the interfaces. Right. Now, this this data is again received by switch number 1. When switch number 1 receives
but the destination MAC address 333 is for that 3 PC only, right?
Yeah, but in the switch 3's MAC address table, the destination MAC is not present. So it is flooding it.
Okay.
It will send it to PC3. It will also send it to switch number 1. Got it? I hope you got that point.
Yeah.
Yeah. So now switch number 1 is again receiving the same data. Switch number 1 is now receiving the same data. When switch number 1 receives it, it sees that now, okay, previously I had received this data on my interface number 1, but now I'm receiving it on my interface number 2. That means it's a new data. It's a new update. So let me update it. It will update it as 2. Okay. Now this was in a clockwise direction. This was in the clockwise direction. Okay. Now let's go from the anti-clockwise perspective. Okay. Switch 1 forwarded the data to switch number 3. Switch number 3 received it. Earlier, it said that, okay, earlier the data was received on interface number 1, but now I'm receiving the same data on some other interface. Which is that interface? It is interface number 2. Okay, it is interface number 2. Now, again, when it does not find the MAC address table, now please remember, by the time this data is received by this, switch number 1 has already sent it to switch number 3. This direct data is received earlier than this indirect data. Okay, so this entry that we see here, 1111 on interface number 2 is actually entered first. All right, I hope that is clear. Now,
and then later that will get updated when the second one comes.
Later that gets updated as 1. Then when it is received from this side.
Okay.
Okay, so over here, it updates it as 2. Now, when it does not see that as a MAC, the MAC address, destination MAC address, it forwards the data. Now it is received by switch number 2. Switch number 2 will again see that, okay, I have received the same data, but now I'm receiving it on interface number 2. So it updates it. It will again not see the destination MAC address and it will also forward. Now, the same data is again received by switch number 1. Now, again, there is an update on switch number 1. Instead of interface number 2, now it has received on interface number 3. This was in the anti-clockwise direction. Right. So if you see here, in the clockwise direction and in the anti-clockwise direction, this data keeps on looping around the network. Even in the clockwise direction be it the clockwise direction or be it the anti-clockwise direction. Okay.
Okay, but
The
how it will
data
come
is
to know? But how it will come to know about the three MAC address, the third one, where it has pinged? Sometime it has to come to know that it one from one it pinged to 3. So
yeah.
how it will come to? It will never come to know that thing that.
No, it will never come to me. That's the reason. By the time PC number 3 responds, the MAC address tables are completely changed. There is no entry that will say that on switch number 1 that the data needs to be forwarded like this. Okay, I'll
Okay.
show you in the like when I do it this in the Cisco packet.
Okay.
I'll
Okay.
show
Bye.
that,
Okay. Bye.
that. Okay. So over here, if you see on switch number 3 also, the data keeps updating between interface number 1 and interface number 2. Over here also, the data keeps updating between interface number 1 and interface number 3. Here also, the data keeps, the first instance was interface number 1. Then the second interface would, the second instances would be, second and third instances would be 2 and 3 for sure, right? So what is happening? Here, what is happening? Let's see that. First, what is happening? Multiple copies of the data is now circulating in the network. Right? That's the first and foremost thing that we can see. Okay. Then the second thing is these multiple copies do not reach the destination. Okay, do not reach the destination. That's the second thing. Third thing, we can see that the MAC address table is unstable. Okay, we just saw sometimes it's on interface number 1, sometimes it's on interface number 2. For other switches, sometimes it's on interface number 2, sometimes it's on interface number 3. The data is received on interface number 3. And we know that the MAC addresses are populated based on the data when it is received. Right? So you can see MAC address table is unstable. Right? Then fourth, now every time a data is received, this switch needs to process the data. Right? Every time a data is received, the switch needs to process the data. Now, if multiple copies are received by the switch, okay, on both the interfaces, it needs to read every data, it needs to process the data and then forward the data. Right. So what is happening? The CPU utilization of the switches it increases. Okay, the switches it increases. Up arrow key means it increases. CPU utilization of the switch it increases. Okay, so these are few factors that you will see in such a scenario. In such a scenario, you will see these factors. That is, multiple copies of the data is circulating in the network. Multiple copies, those same multiple copies do not reach the destination, and because they do not reach the destination, MAC address table of all the switches involved, they're unstable, and because of that, the CPU utilization of the switches it increases. This collectively, these all collectively are called as broadcast storm. A broadcast storm. So if someone asks you what is a broadcast storm, just tell them that same copies of the data is circulating in the network. Those copies do not reach the destination. The switches MAC address table are unstable, and the switches CPU utilization increases because of the broadcast storm. Okay. So why does this happen? First of all, the reason is that all these three switches are interconnected. All these switches are interconnected. Now, a question. What can we do in order to avoid this broadcast storm? What can we do in order to avoid this broadcast stomp? Any guess? Okay. So
Sure.
in order,
Not sure.
yeah, go on.
Yeah, not sure.
Okay. So in order to avoid this broadcast stomp, what we can do is we can remove one of the links. We can remove one of the links. Okay. Now let's see what happens if you remove one of those links. So the same thing, PC1 sends the data, switch 1 makes an entry saying 1111 was received on interface number 1. It does not see the MAC address table. Sorry, it does not see the destination MAC address in the MAC address table, and it is going to forward it. Switch 2 receives it. Switch 2 makes an entry 1111 was received on interface number 3. It does not see the destination MAC address. It will forward it to only PC2. It does not forward this out of interface number 2 because there is no link present. Okay, then this data is received by switch number 3. It makes an entry 1111 on interface number 2. It does not see the destination MAC address, and hence it forwards the data to PC number 3 only, but it cannot forward the data out of this link because there is no link present. So here what happens? PC number 2, okay, obviously PC number 2 will drop the packet because it does not receive, that's not the MAC address. It will drop it. The data that is sent across this link, which is avoided. So switch number 3 is not going to receive the data from some other interface. Similarly, the data that was sent earlier to switch number 2 from switch number 3, that is also avoided. And again, switch number 2's MAC address table is not going to change. So if you see here, your MAC address table now is completely stable. There is only one entry. There is only one entry. There are not many or multiple entries. And also, because one link is completely removed, multiple copies, these things, multiple copies are not present. Multiple copies, obviously, since multiple copies are not present, okay, this particular statement is not valid in that sense. Okay, one copy, multiple copies created, but out of those multiple copies, one of them reaches the destination. Okay, the MAC address table is unstable, which now is currently stable. Because the MAC address table is currently stable and there are no multiple copies created, the CPU utilization is also stable. And you are completely avoiding the broadcast stomp. You're completely avoiding the broadcast stomp because you removed one of the links. Okay, so this is what happens when basically there is a loop in the network. When there is a loop in the network, you will see a broadcast storm. And as I said, this is purely for layer 2 network. This is purely for layer 2 network. You will always see a broadcast storm. Clear what is a loop? What is a broadcast storm? Any question there?
So when this second link is not there between the 2 and 3, then in that case, when the PC1 ping to PC3, and data will not be dropped, so it will be accepted by PC3.
It is accepted, but it was accepted earlier also. It was accepted by PC3 earlier also, but by the time PC3 responds and PC3's data, actual data reaches here, this entry is updated by some other interface. Either it is updated as 2 or it is updated as 3. So what happens? Switch number 1 will either forward here or switch number, if the data is being sent like this, switch number 3 will forward the data here. If the data is coming like this, the switch will forward here.
No, that means the reply comes from 3 to 1, but in that case, it doesn't accept the reply because the port is different. Now it
Updated.
replies to the port 2, but the port 2 is not present. It has changed to 3. So the port 3 is not
Exactly.
there. It will forward that again back to 2.
Exactly.
The reply from 3, it will forward again. Oh, that way it will keep on moving. Okay. But because the port is keep changing, the MAC port and all those things keeps
Exactly.
changing.
The MAC
That's
address
why it is
port keeps changing.
okay. That
Okay.
means it
So
replies, it stores also, but it again forwards because it's not able to accept that thing.
exactly.
Okay. Okay, got it now. Yeah.
Okay. So that's what. So by the see, PC1 sent the data. Okay, it is received here.
Mhm.
PC1 has sorry, not PC1. Switch1 has also sent the data over.
The switch to also.
Switch2 also. Okay. Switch3 forwards data over here. Switch3 forwards data here also. Again, switch2 forwards over here. Switch2 is also forwarding over here. Let me change the color. Let me change the color for clockwise and anti-clockwise. So it is better to understand. Okay. So switch 1 is receiving the data. Now, switch 1 will forward the data to switch number 2. Okay. Switch 1 will also forward the data to switch number 2. Switch 3 receives it. Switch 3 will forward to switch number PC number 3. Switch 3 will forward to switch number 2 also. Switch number 2 is also going to do the same thing. Switch number 2 forwards the data to PC number 2. Switch 2 is also going to forward this data to over here. So over here on switch number 3, you see earlier it received this data on 2, but when the data is coming from switch number 2, now it needs to update this entry. Similarly, on switch number 2, earlier the data was received on interface number 3, but now the data is received on interface number 2. Okay, then again, switch 2 will forward this data over here. Correct. Switch 2 is going to forward the data over here. Similarly, switch 3 is also going to forward the data over here. By that time, what happens is that by the time PC3 responds, this entry, this first initial entry of interface number 1 is overwritten by either the newer updates, that is either interface number 2 or interface number 3. So every time a new data is received or a new update is received, it keeps changing the entry. So now it was received on interface number 2. Then again, in the anti-clockwise, it is received. So this entry is removed, new entry is entered with 3. Then again, it is received in the other direction, 1 1 1 1. So again 2. Again, a new entry is received from the opposite side. This will be for 3. So like this, not only for switch number 1, for switch number 2 also, the MAC address table keeps on changing. For switch number 3 also, the MAC address table keeps on changing every time the data is received from the other interface. So this is what I said, loop. Multiple copies of the same data is circulating in the network without reaching the destination.
Anywhere, just without reaching the
destination. Without reaching the destination. Got it?
Got it. Yeah.
So we can, as I said, we can completely avoid this particular broadcast storm by removing one of the links. Over there. So if I remove this link, let's think from this perspective. If I remove the link between switch 1 and switch 2, what is going to happen? PC1 forwards the data. Switch 1 makes an entry 1111 was received on interface number 1, and it does not see the destination MAC address. It will forward the data to switch number 3. Switch number 3 will make an entry saying 1111 was received on interface number 2. It does not see the MAC address. It is going to forward the data to PC number 3. It is also going to forward the data to switch number 2. Now, switch number 2 makes an entry saying 1111 was received on interface number 2. Switch number 2 does not see the MAC address entry. It will forward to PC number 2. But now in this case, when PC2 drops the packet, okay, here PC3 will respond because the data is for PC number 3. But here PC3, it will respond. But when it responds, the data is stable, or the MAC address table of other switches is stable. MAC address table of this data or these switches is stable, and hence now when switch number 3 responds, it is going to forward the data out of interface number 2. Switch number 2, switch number 1 receives it. Okay, and then what it will do? It will forward the data back to PC number 1. So we avoided, as I said, we avoided this broadcast storm because we removed one of the links, one of the looping links over here. Got it?
Yeah, got it.
Yeah. Now, this was with just one topology, meaning with 3 switches. Okay. What if there are obviously like in a data center where there are 50, 60, 100, 200 switches all together setting, right? And we know that multiple switches are connected to each other. They are connected to each other. Now, in that scenario, what can happen? If I start to remove the links, let's say there are 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10, 11, 12. These are switches. Okay, let's say they are interconnected. Something like this. They're interconnected. Okay, this is just a rough diagram. They're interconnected. Now, if I want, okay, a loop-free environment. Okay, so over here, when I removed one of the links, it's called as a loop-free environment. Okay, there is no loop in the network. It's a loop-free environment. Now, in such a network where there are so many switches connected together, creating a loop-free environment manually where I have to remove few links is a tedious task. Not just a tedious task, it's a very risky task as well. I can remove, let's say, if I remove one of the links, for example, let me give this. I removed one of these links. There's a chance that if I remove these links, there is a traffic drop. Some users are not reachable to each other. We are humans, we can make mistakes. So there is a chance that I can remove one of the links where critical users are sitting and those users are now not connected to the internet. There is a high chance. Okay, or let's say if I remove multiple links, not just one link, I just removed multiple links. So again, there is a chance that the traffic path, okay, let's say previously these two were connected. Okay, previously the users were able to talk directly because the traffic was going like this. Direct connectivity was there. A direct traffic path was present between these two switches. Now, because of the loop, I removed one of these links. So now the data is taking a longer path. The data is taking now a longer path. Okay, which may be necessary, which may not be necessary to avoid. But again, as I said, we are humans, we can make mistakes. Right? So in order to avoid such mistakes, right, we created an automatic mechanism. We created an automatic mechanism which will help the engineers create a loop-free environment on its own. It will help to create a loop-free environment on its own. And that particular feature or that particular protocol was called as spanning tree protocol. Okay, so spanning tree protocol is a protocol which automatically creates a loop-free environment. Okay, all we need to do is configure spanning tree on these switches, and they will automatically create a loop-free environment between themselves. We don't have to do anything. obviously we have control over spanning tree protocol. We can change the direction of the traffic. We can change how the traffic flows, etc. But we'll talk about that later. However, spanning tree protocol, as I said, it's a what do you say? Dynamic protocol, okay, which helps to create a loop-free environment into layer 2 network. This is a layer 2 protocol. It's a layer 2 protocol. You will hear this out of my mouth a lot. Okay, layer 2 protocol, layer 3 protocol, meaning they run or they forward or they run based on MAC addresses. That's why it's called as a layer 2 protocol. So we created spanning tree protocol in order to help us create a loop-free environment automatically. Okay. Now, with the word tree, okay, let me draw a tree over here, a rough diagram of a tree. These are the roots. Okay, these are the branches. Okay, and these are the leaves and whatever. So this is the root. This is the trunk. Right. These are branches, and these are leaves. Okay. So we know that in a tree, we know that the root is the most important part of the tree, because this root is connected to the ground, and from the root only the tree or any plant, it fetches water and it distributes to the whole tree. Okay, so root is the most important part of the tree. And if we know that if we take out the root, if we completely take the root out of the tree, basically the tree is dead. Right. So root is one of the important part of a tree. Similarly, think of a human brain. Okay, I am drawing a human brain. Okay. It's a very rough diagram. Okay, so I believe human brain probably looks like this from the side. Okay, this is a side view, not the front view or an upper view. This is a side view. Okay, so this is a human brain, right? And human brain is connected to the spinal cord. Okay, it is connected to the spinal cord, and through the spinal cord there are a lot of nerves. There are a lot of nerves which are connected to every part of our body. Okay, this is our brain, and brain basically sends signals. Okay, it sends electric signals or electric pulses to the spinal cord, and it is sent to every part of the body, and based on the instruction the body reacts, and whatever the body reacts, it is also sent back to the brain to process further. Right. So again, brain, we can call it as a root of our body, and it is the most important part of the body. If there is no brain, basically we are dead. Right. Similarly, in the spanning tree protocol, as there is a word tree itself, right? So if a spanning tree protocol is present, then there should be a root in the network. Okay, then there should be a root in the network. And this root is nothing but a switch. We call that as a root switch. This root switch is responsible, as I said, root, the word root means important part. This root switch is the most important part of the network. And this root switch will control the whole layer 2 network for spanning tree protocol. Based on this root switch only, a loop-free environment is created. Okay, any question till here?
Not really.
Okay. Now, as I said, spanning tree protocol is a automatic or a dynamic protocol. whatever it does automatically. We don't have to intervene. We don't have to intervene. Okay. Give me a minute. Sorry. Okay. So it's a root switch, as I said, and it controls the whole layer 2 network. And as I said, it's a dynamic protocol. So obviously the root switch is supposed to it's a dynamic protocol, and spanning tree protocol runs automatically. If it runs automatically, that means the root switch should be elected. It should be elected, right? You cannot just if it is a dynamic protocol, there should be some mechanism between the switches to find out who should be the root switch, right? Sim- so as a so in a spanning tree protocol, these switches, no matter how many switches there are, there can be 2 switches, there can be 10 switches, there can be 200 switches. Out of these 200 switches, one of them becomes the root switch, and for that an election happens. Election of the root switch happens. It's just like how how we elect our leaders. We vote, right? Similarly, here also a voting kind of thing happens, and based on the vote, the root switch is elected. Okay. So what is the voting criteria in this part? In a spanning tree protocol, what is the voting criteria to become the root switch, to be elected as the root switch? What is the voting criteria? The first and foremost criteria is that A, whichever switch, which no matter, as I said, no matter how many switches are there in the network, whichever switch has the lowest spanning tree protocol priority, it becomes the root switch. Okay, so election of the root switch happens first based on the lowest spanning tree priority. So spanning tree priority is basically a number. Is basically a number. Okay, and that number ranges from 1 to 655 65535. This is the range of priority numbers in the spanning tree protocol. So if there are 200 switches, out of those 200 switches, whichever switch has the lowest priority, the lowest is 1, the highest is 65535. Out of those 200 switches, whichever switch has the lowest priority becomes the root switch. Okay. Now, by default, by default, the span every switch. Okay, I'm talking from a Cisco's perspective. Every Cisco switch by default has a priority of 32,768. This is the default priority. So every Cisco switch has a default spanning priority of 32,768. Okay. Now, as I said, it's a default priority, meaning that the moment our switches are powered on, okay, and if spanning tree is running on them, they will set a priority of 32,768 as the spanning tree priority for themselves. Now, if all the switches in the network have a default priority of 32,768, then who will become the root switch? Because the first condition says that the lowest priority will be the root switch. But if all the switches have the same priority, then who will become the root switch? Right? That's a tie. So for the second thing, the tiebreaker then becomes whichever switch, if the priority of all the switches in the network is 32,768, or even if the priorities are not same, but the lowest priority, is a match. So let's say there are 10 switches in the network. Okay, few of them have the priority of 32,768. Few of them have a higher priority than 32,768. Few of them have a lower priority than 32,768. Let's say those fewer devices or fewer switches are two. Two of them have a, let's say, priority of 4096, for example. Okay, two of the switches have a priority of 4096. That means that is also a tie. Okay, in that case, when the priority is a tie, the next tiebreaker is that whichever switch has a lowest MAC address, that becomes the root switch. That becomes the root switch. Okay, clear? Any question?
Okay, so from if suppose 10 switches, 5 of them having this, 3 of them having little less, and remaining 2 has more less. So it will go
Okay.
towards the lowest one. And from that also, if it is equal, then we have some other process. If only
then
one
it
is
will go for
smallest,
the lowest MAC.
if only one is
Out of
smallest,
those,
then it will. Okay, select.
yeah, if one of the priority is the smallest and there is no equivalent switch to it, then that switch will be chosen as the root.
Okay.
So let me draw the diagram and show you. So switch number 1, switch number 2, and switch number 3. Okay. I'm not drawing PCs. MAC address of switch number 1 is 1111. Switch number 2 is 2222. Switch number 3 is 3333. Okay. And let's assume that the default priority, let's assume that all the switches have a default priority of 32,768, 32,768, and 32,768. Okay. And as I said, it's a default priority. That means I can change the priority also. I can change the priority also. So let me change the priority of 32,768 to, let's say, 65535, the maximum one. Okay. And let me change the priority of 3 as 4096, for example. So in this case, what is going to happen? Switch number 3 becomes the root switch because it has the lowest priority. Because it has the lowest priority. Out of these 3 switches, switch 3 has the lowest priority and hence it becomes the root switch. And as I said, all these switches by default have a priority of 32,768. So switch 2 also has a priority of 32,768. Switch 3 also has a priority of 32,768. Now in this case, since the priority is a tie, we will go for the lowest MAC addresses. We will go for the lowest MAC addresses. So out of these 3 switches, switch 1 has the lowest MAC address and hence switch 1 becomes the root switch. Switch 1 becomes the root switch. Okay. Now we know that in real world, obviously the MAC addresses won't look like 111122223333. No. Okay. This is not how the MAC addresses would basically look like in the real world. They look different. Correct. So in that case, how do we know which one is the lowest MAC address? So you can see here, these two are MAC addresses: B8, B7, DB, 3C, 72, 38. This is one of the MAC addresses. The next one is F4, A4, 75, 07, 2E, 6B. Okay. Now, the MAC addresses, when it is compared between the switches, when the MAC addresses are being compared between the switches, it is compared from left to right, digit by digit. One hexadecimal number at a time. From left to right, each and every hexadecimal digit is compared. So over here, let me write it down: B8, B7, DB, 3C, 7238 is the first MAC address. The next one is F4, A4, 7507, 2E, and 6B. Okay, these are the two MAC addresses. Out of these two MAC addresses, which is the lowest? So as I said, the switches compare the MAC addresses hexadecimal number, every hexadecimal number by hexadecimal number from left to right. So the first hexadecimal number is compared, that is B and F. In hexadecimal form, we know that it starts with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is written as A. Okay, 10 is written as A, B, C, D, E, and F. So 10, 11, 12, 13, 14, and 15. Okay, so over here, we can easily see that B is lower than F. B is lower than F, and hence this MAC address is lower. This is the lower MAC address. So digit by digit, every like a hexadecimal number is compared, and out of those, whichever is lower, it is chosen as the lower MAC address. Now, what if this is also F4? The first two digit is also F4. So F4, 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 F4. It's same, right? The next, third, B and A is compared. Out of B and A, obviously A is lower. That means this MAC address is the lower of it. This MAC address is the lowest or lower MAC address in the two, between the two. Clear? Any question how a lower MAC address is chosen?
No, it's fine. I already knew this one. This is good actually. So from left to right, it will go and one by one. So one, whichever finds first smallest, that will consider as a small.
Smaller, yes.
Okay.
So over here, as I said, to keep things simple, I'm just assuming the MAC addresses as 1111, 222, etc. So over here, in our diagram, the root switch is switch number 1. Okay, and we are keeping the default priority of 32,768. Default priority of 32,768. So when a default priority of 32,768 is taken, if it is a tie, you cannot just default. If the priority of the switches is a tie, then the lower MAC address of the switches is found. Whichever switch has a lower MAC address, that becomes the root switch. Clear?
Yeah, it's
Yeah. Now, what's the time? It's 11:30. Okay, we'll continue the spanning tree protocol tomorrow. Okay.
okay. So we're pausing it here. Okay.
Yeah, we'll stop our session here and then we'll continue. All right.
So
This
till
is
here
already
is
11:13.
till here is the identification of this. Okay. Okay. So from tomorrow it will be like 5 o'clock or
Let me check for a stop. Stop.